development of the SimuFest application, our team of engineers made a few assumptions to make our product simple to use and work smoothly. A festival can often be naturally broken down into various zones associated either with a stage or with a main merchandise area. Each zone will likely have their own food vendors, restrooms, merchandise stands, and other various services specific to the festival. First, we assume each zone is self-contained, so that the flows in and out of each zone are roughly the same, and arrival rates at different stations are only dependent on if there's a concert going on. We do not account for how a show's popularity might affect zone flow. This could overestimate the amount of people in the zone at certain times, but this is justified because we care most about the proportion of people waiting above a certain threshold time.
We assume that queues for the same type of vendor in a given zone will fill uniformly regardless of popularity or brand. We also assume that once in line, customers will stay in line. The uniformity gives our model its speed and simplicity, and it's justified by the large number of people present. If uniformity becomes a concern, our model is flexible enough that the festival planner can run another simulation that separates vendors based on popularity, adjusting arrival rates accordingly. We assume arrival rates occur according to a process process and that service times are distributed uniformly. We thin the arrivals according to the input schedule with the assumption that more arrivals occur between shows.
Our model is based on a non-homogeneous Poisson process with two different arrival rates. The concept of thinning allows us to generate arrivals at the maximum rate and then accept a proportion of generated arrivals equal to the current rate divided by the maximum rate. Our run is initialized with the given values for queue length, number of servers, arrival rates, and show start and end times. The run event schedules the first max R event. The max R vertex then generates arrivals at the peak rate. These arrivals are thinned by scheduling enter events with probability equal to the ratio of current rate to max rate. After a person enters the queue, if there is an available server, then they start service immediately. After a random service time, people complete their service and leave. When a job departs, if there are more people waiting in line, then another customer starts service.
We have developed a simple and easy-to-use web interface for our simulation. Users are first directed to a splash page, as you see here, with a brief description of our product. Clicking through, the user is then prompted to input the specifications for their desired simulation. For a given run, the user chooses one type of service they want to simulate. Our default values are representative food vendors, with arrival rates reflecting the fact that more people eat between shows than during a show. Arrival rates can be gathered experimentally for more accurate simulations, and the number of available stations can be varied to determine ideal waiting times for customers. The user can customize the concert scheduling for up to 10 shows, keeping note that all times are in minutes with reference to the beginning of the event. For schedules with fewer than 10 shows, the remaining fields can be left blank. After inputting the specifications, the user can click this button to begin their simulation. When the simulation finishes, users are redirected to an easy-to-read output page. First, we display a confidence interval of the average queue length calculated by several trials of the simulation, then a graph displaying the size of queue throughout one sample run. As you can see, there are distinct peaks throughout the day around the time of concerts due to several assumptions about the flow of the festival.